Okay, so we had the definition of a covariance matrix of a vector. So we have a vector y. In this case, it has three coordinates. These are all random variables, and the covariance would be a 3 by 3 matrix. The diagonal entries would be the variances of the coordinates, and then the off-diagonal elements are the cross covariances. So 1, 2 elements that we get, or just the covariance and cross covariance that we know. So would be the the covariance of y1 and y2. And immediately, if you look at this, you notice that these off-diagonal elements, because covariance is symmetric, will be the same. So this one, for example, covariance of y1 and y2 is the same as y2 and y1. Covariance of y1 and y3 is the same as y3 and y1, and the same for the other off-diagonal. So if you look at the mirror image across the diagonal, it's the same. So this gives us the first property of the covariance matrix. So the covariance matrix is symmetric. Okay, which means that sigma is equal to sigma transpose. The other feature that we notice is if the elements of the vector y1 and y, and let's say are pairwise uncorrelated, then sigma will be diagonal because all these off-diagonal elements would be 0. Okay, all of them would be 0. And then I just get the diagonal, covariance. So the diagonal covariance matrix is the same as saying the coordinates of the vector are pairwise uncorrelated. An important special case is that if they're all pairwise uncorrelated and have equal variance, like the coordinates, so if the variance of all the coordinates is also, let's say, equal to sigma squared, all I, then what I get is like, in this case would be like, this would be sigma squared, 0, 0, 0, 0. Everywhere, and then I can factor out sigma squared times identity, 3 dimensions. So it's like I3 here is what do you mean? A 3 by 3 identity matrix. So IN in general would be an n by n identity. So just the covariance matrix would be the scaled multiple of the identity, and that scale would be sigma squared. Okay. This is going to be important for us in regression because the typical assumption in regression is that we'll see the noise vector has covariance which looks like this, sigma squared by. Which then you can interpret as saying that the coordinates of noise have equal variances and they're uncorrelated. Okay. Does that make sense for people? This is nothing fancy, it's just a consequence of the definition, uncorrelatedness and the covariance. Question? Okay. The last property is perhaps not very obvious, but it's very useful. What it says is that what happens if I multiply y is the random vector here. If I multiply it by scalar alpha, this would be a scalar. What do we mean by a scalar? Scalar. It's a number just in R, right? As opposed to a vector. And when they say scalar, just a number. Just one element. In contrast to vector, usually it's used in contrast to it. It's a scalar and also constant. So alpha is non-random. And also we have a vector which is non-random. So if I scale y by alpha, that is another random vector. If I add d to it, d is of the same dimension, I get another random vector. So alpha y plus d is a random vector, it has a covariance matrix. And this identity tells you what the covariance matrix is in terms of the covariance matrix of y. In particular, it would be alpha squared, it comes out squared, and covariance of y plus b would be gone. Okay, so a constant shift does not alter the covariance matrix. And if you recall, so the little proof of this is if you recall the covariance of y was, we proved the formula, which was like y tilde transpose. Expectation of this. If you remember, what is y tilde, if you recall? Yeah, so it's the centered version of y. So y tilde would be y minus its mean. And so this process of removing the mean would remove any constant b. So if you construct, let's say, y plus b, this will not change because b will be the same. It comes out of the expectation, it gets canceled out. So centering remove the shift. And so this quantity remains the same. And also you can see if I multiply by alpha, both the mean and the variable are multiplied by alpha. So this y tilde gets multiplied by alpha. So you get alpha y tilde and alpha y tilde squared. Right, transpose and then alpha squared from that. Okay, so it's like a short proof via just the identity we had the definition, just the definition before anything. Sounds good. So this property is very useful. Shifting does not alter. In particular, shifting does not alter the variance. Neither the variance coordinates nor the variance. So shifting variance. But as you can see, like it's scale, not scaling variance. So is shifting variance. But not scaling variance. There is like a corresponding thing which is scale invariant also. Remember, so the univariate case, what is the scale invariant version of the covariance thing or covariance? Scale invariant. I think that covariance is to a scalar invariant object. Anyone? There is covariance, and then there's some other quantity which is very much related to the covariance we discussed. Divide by certain things. Correlation. Correlation is a scale invariant. So there is actually a correlation matrix similar to this, which I'm not going to define here. The correlation matrix will be a scale invariant as well as shift invariant. So equivalent, you can say that correlation matrix is just, we'll have ones on the diagonal, and then replace the covariances with the correlation coefficient. And that will be, maybe that will be a good exercise for you to try. Exercise. This is for me to remember. Correlation. Matrix. Questions? So now we're going to do a very important property, which is like a kind of generalization of this fact. If you remove b, you get alpha y times will be alpha squared times 4 y. So sorry, for covariance of y. So a sweeping generalization is what happens if I compute, I want to try to compute covariance of ay, where a is an increase. Okay, I can do that. So y is a random vector, a is a deterministic matrix. I can ask what is the covariance of ay. Let's say a is m by n. So we did figure out what this is like non-random, and ay would be n-dimensional. We figured out what the expectation of ay is last time. Now we want to figure out what the covariance is, and that above, or just here, it gives you the formula. It's a little bit non-intuitive, so you get a sigma a transpose. So a comes out. In particular, if this was just a like alpha, you get alpha sigma alpha transpose to the alpha. And then because alpha is a scalar, you can just pull everything together with alpha squared times sigma. You get like that result. But this is more general. Is this setting kind of clear? I have a random vector y, and I have a non-random matrix AY, so A times Y, as we've seen before. So AY would be m by 1, so m by 1 vector. And so the covariance has to be m by n. And if you verify this middle thing is like m by n, and this is m by n, and this is n by n, so it matches. So let's try to prove it and we'll see. So how do you prove this? Proof. One. Variance of AY. Let's call AYU. Okay, I'm gonna call this a new random variable u, so I want the covariance of u. And I'm gonna give you a hint. I'm just gonna use that formula, simple formula, u tilde u tilde transpose. Make it this expectation of u tilde transpose, where u tilde is where u tilde is u minus the expectation of u. Okay. So I want to simplify this a little bit. Anyone can tell me what the expectation of mu would be? Fine. What is the expectation of u? One. Yes.
Is the expectation of AY, the expectation of Y.
Expectation of AY, which would be A times the expectation of Y. And why is that? Linear expectation. Yeah. So this is guarantee of expectation. What was your name, by the way?
Yeah. Aiden.
Aiden. Okay. Good. So this is what we did last night. Okay. Now, if you notice, AU is also AY. So what kind of simplification can I make? AY minus A times the expectation of Y. In order to know there's some kind of interesting factorization that we can do. AY minus expectation, that's like A times expectation of Y. Yeah.
Factor out in A.
Yes, factor A out, so like I get Y minus expectation of Y. So what do we call this?
Y tilde.
Y tilde in our notation. So I got A times Y tilde. So as you can see, like just the relation between the center version of U and the center version of Y is the same. So it's just kind of like true, like the same transformations apply. So now I do this little calculation here. Now I go back to the original one. So I'm going to plug this in here. So I get expectation of A Y tilde and then A Y tilde transpose. So what can I do now? So what is AY transpose? And then have an alternative expression. So what, let's say I have like matrix A and a matrix B and I do the transpose. So what happens? Okay, this way. What does the transpose do with product of interesting? Yes, so you get B transpose A transpose. Second. And T. Right? Operation anti-permutation. Okay. So it's just the border. So what I did here, what do I get? If I do this, I'm gonna get AY tilde, and then assuming you know like y tilde, a tilde, just use that identity. Now, what can I do next? Do parentheses matter in matrix multiplication? So I can basically parentheses don't really matter, so I can just drop them and put them anywhere I want. So maybe you can have a giant expression like a y tilde transpose a t, and then you can do it in any order. And you can make products in any order. So what is the natural way to do it? Natural way is to put it here. Okay. This is like a middle matrix, so I get A times this middle matrix times the transpose. And that middle matrix is random. So anyone remember an identity that we can use here? A y tilde transpose, y tilde transpose, let's say this is like a random matrix. So what should we do now? It was, yeah.
You can take out the A.
Yes. So I can take A on this side and A transpose on this side, and then apply just the expectation to the middle guy, which is the random quantity. Why is that?
They're not.
They're not random, but like the keyword here is what property of expectation are we using? Linear, yes. So you do say linearity, like works now 90% of the time. Yeah, that's 10%. So what's your neighbor?
Right.
Right. So are we done here, or do you improve there as well? So what is this guy? Covariance matrix of y, which we call sigma. So we prove that the covariance matrix of mu is A times covariance matrix of y times A transpose, which is what we want to do. Okay, so we use the linearity of expectation twice, once in kind of figuring out the relation of the centered version of mu with y, and then another times when we try to do the final kind of calculation. Okay, there's just a consequence of properties of matrix vector multiplication. There's just matrix multiplication and linearity of expectation. Okay. Question. So I encourage you to go through this proof. If you didn't follow it, just ignore it. Read the previous lecture, try to prove it from first principle. You don't have to define mu, you can do whatever you want, just based on the definition of covariance matrix, try to prove this, and you would get comfortable with this matrix vector board of calculation, random calculation. You have random matrices, random vectors, and you want to compute the covariances of samples. So why this is important for us, if you've seen the regression in the previous course, since you've seen, so beta had the coefficients of regression would be like a matrix times y, where y is random. And so if you call that matrix A, it would look like this, so A times y, and then you calculate the covariance matrix of beta hat, based on the covariance matrix of the opposition. It's like a key property that we're going to use. Right. Just be on the lookout for this. Let's do an example. It becomes a little more clear. So x1 and x2 are random variables. Each have variance of 1. And then there's a covariance of rho. This is a similar situation to what we had last time. And then what I want to do is I want to form this new vector x1 plus x2 and x1 minus x2 and compute the covariance matrix of it. So this is new vector z. And if you can just check, I just write it as this matrix 1, 1, 1 minus 1 times x. And x is just x1, x1, x2. Just do the matrix multiplication, it's really clear. Okay. So if I want to calculate the covariance of Z, I'm going to use that formula A, and then covariance of X times A transpose, and then I get 1, 1, 1 minus 1 times the covariance of X is 1 row, row 1, because the diagonals are the variances and the off diagonal is the covariance. And then I'm going to transpose this in 1. I mean, it happens to be like symmetric, A is symmetric, so you take the thing. So can anyone help me multiply this out? It should be better at me doing this calculation. So just write down the formula, just notice that the variance of X is this, and then multiply it out. How do we multiply it out? Whichever way you want to multiply it is fine. You can multiply the first two, then times the second, or the last two, and then multiply with this, or someone help me do it. Or I'm going to do it myself and my own way. Just the way that like yes. The outside one first. The outside one first, I think. Can you tell me what it is?
Yes, this would be 2 upper left.
It wouldn't be 2. Like would be like this. Upper left. Yeah.
Yeah, so 1 plus P.
1 plus row.
Yeah, 1 plus and then row plus 1 to the right.
Row plus 1.
Row, the row minus 1.
1 minus row.
Yeah, that's right.
And then row minus 1. Right. Okay. And then can anyone help me do that other one? I'm gonna assume that you know how to do it, so I'm not gonna spend too much time. So 1 plus row times 1 plus some of this would be this times that. Okay. So I get 2 times 1 plus row. And then what happens to the other one? And then multiply this by that. 1 plus 0, yes. And then this one you would know that it would be 0 because it has to be symmetric. You can just double check that. If you're doing the exam, I mean, it depends on that they're mismatched and something wrong. And then what is the last one? You get 1 minus row, and the other one flips the sign, you get 1 minus row. Squared, is that true? Correct? No. What did I get? 3 times 1 minus row, yes. 2 opposites, yeah. Okay. Done, right? So if you go back to the previous lecture, this one we calculated by hand using linearity directly, and then this one as well. And this one we got for free. Okay, so we calculated the variance of this quantity and the covariance of the pairs. This time, this covariance matrix gives you that those values in addition to also the variance of 1 plus 6. Okay. So when you want to calculate everything, this approach is maybe faster. If you just wanted this, or just wanted this, it might be just using linearity directly calculate that quantity we can use here. But everyone happy with this? And then you can do medians of examples of this. This doesn't have to be, for example, 2 by 2, it should be like I could have defined like a, I don't know, 4 by 2 matrix, whatever. Linear transformation to get any coordinates and the tools would work. Okay, so let's move on to one last property. So covariance matrix is always positive semi-definite. Okay, if you have gone through the discussion, you would know what this means, or you know, from all sorts of anyone remembers that it's positive semi-definite. How many people have gone through the discussion? Okay. So you should probably have seen it. What is the positive semi-definite? So if I have sigma, and I claim that it's positive semi-definite, it means if I pick any u and do u sigma u transpose u is a vector, say in Rn, sigma is in Rn, but again, this is going to be always not negative. Okay. This is like quadratic form. U sigma u transpose is always not negative. And this holds for any covariance matrix. The way to prove it, or let's say let's do A, for example. This is deterministic. So let's say I have y random, and then sigma is the covariance of y. So what I would do is I want to prove that A transpose sigma A is non-negative. So is this true? So I'm going to look at this. This is A transpose covariance of y, A. And does this resemble something that we just did? And I write this in a different format. See, the identity that we just used using an alternative form to it. Yes. The covariance of A transpose y. Why? Because A transpose comes out on this side, and then A transpose comes on the other side. Okay, this is just an instance of what we just did. The other way, okay. So this gives me, this is really A transpose cov y A transpose transpose. Like that result that we had, and so it's. So what is the dimension of this? So y is going to be Rn. This is going to be in Rn by n. And A is going to be in Rn as well. So what is the dimension of this quantity? A transpose y. I have a row vector times a column vector. This is going to be A multiplied by y. What is the dimension of the result? 1. So it's a scalar. And so the covariance matrix of a scalar, what is it? This has one element. I mean, a scalar is technically a 1-by-1 matrix, so it has a covariance matrix, which happens to be. Sorry?
A square.
Square? Oh, you're going to square. It's a square, so 1-by-1 is a square matrix. But what is that element? What I'm looking for is just saying that is this just the variance? Just the variance of this quantity. Can variance be negative? No, variance is always non-negative by definition. So we prove that this quantity A transpose cov ya is going to be always non-negative because the variance of A transpose y is going to be always non-negative. So this is true for any A, hence proves that sigma is positive semi-definite. The very important property of variance here. It's like the equivalent of variance being non-negative in general. Like sigma is like a multivariate values. And for a matrix to be non-negative, I mean, you can't have element-wise entries that are non-negative, but this is better. This is the matrix. The sigma can have negative entries. But in the world of matrices, this is a more natural notion of non-negative. the sigma can have negative elements, not on the diagonal, but off diagonal, but it's still going to be positive semi-definite. All good. I'm gonna maybe ask the TAs to go over this a little bit more. Proof is just one line, the consequence of this fact applying in a very special case. You apply to A transpose Y. So this would be A transpose. And then you get that this is always going to be a combination of the fact that the variance is non-negative and this property tells you that sigma is positive semi-definite. The positive semi-definiteness has a lot of interesting consequences. I mean, for example, all the eigenvalues will be non-negative. And we find with semi-definite because the property that all the eigenvalues are negative. If it happens that some of them are zero, then you land in this pathological case, which I'll let you read if you have questions. So if things are not pathological, they're all symmetry. Strictly to get a zero, in that case, the matrix would be positive definite. So semi means it could be zero. So an inequality could be, for some A could be zero, and that corresponds to like the and that corresponding eigenvalue to zero. But in general, they're always a negative. Eigenvalues can't be negative. Sounds good. So you know a couple of things about covariance matrices. They're symmetric, they're positive semi-definite, and you know how to like how they kind of transform under linear transformation. So that line is telling you how to. So this is kind of all we kind of need, more or less. And from this you can get a lot of interesting problems. Questions about this? How many people have seen positive semi-definite matrices elsewhere before? Okay, good. So for other people, if you hear a question, this is not a trivial concept, but once you like stare at it and work with it, it becomes kind of rather like natural, like non-negative number. Just remember that it's not element-wise non-negative. It doesn't say that the elements are all non-negative. It's something more interesting. Elements can be negative, but these linear forms that you form, these are going to be non-negative. So you form these kind of, they're not linear actually, they're quadratic function. Okay, I'm going to move on. There's this slide about the correlation, which I'm going to skip. Let you read it. And so there is a particular transformation that you can do, which is related to the positive, like the square root of the matrix. So if you take the square root inverse of sigma and apply to y, use that identity, you can show that the covariance, the result would be identity. So this operation decorrelates. They get like a new vector, which kind of is related linearly to y, but is like normalized in the sense that the variance is all one, and the off diagonal unassociated. So sometimes called y-caning or decorrelation. And it's useful at some point in the course, but you're not going to use it as much. The properties of the spectral decomposition in defining what the square root is are useful. So if the P hasn't covered it, I would ask you to cover it. And I'm just gonna leave it there. You can read it, and you may come back to it. But basically, you can use this property to construct. We find the linear. Just you will find A such that the other side is identical, and that A, for example, could be the inverse of the square root of the covariance matrix of Y. So there exists a linear transformation that does that for you. There are multiple actually linear transformations. Okay, maybe not. Anyway, so maybe you have known enough about random vectors, random matrices, and covariance matrices, which are very interesting. And now the last piece that we need before we kind of dive into regression is this idea of a multivariate normal distribution. How many people have seen a multivariate normal? What is multivariate normal distribution? What is the normal distribution? That's univariate. I have a random variable. So it's a distribution for a random variable. So we say, for example, x has a normal distribution between mu and variance sigma squared if it has its density. So it's enough to define the density. So if you want to define the statistical properties of the random variable, just tell me what the density is, then I can figure out the probability of any event that I want. So, but when the probability that x lies in, for example, -1 and 2, I can just count the -1 and 2 and I integrate. And that's all we need to build the probabilities of events. And so if you give me the density, that's enough. And so this is a two-parameter, two-parameter family of distribution. So it has a mu mean, if we often write it mu, and it has variance, which we often write as sigma squared. And this is the form. Hopefully you've seen. How many people have seen this form? Okay. So what does it look like? Sorry? What does it look like?
Normal.
It looks like a normal, but like
Over.
bell curve, yeah, okay. It's like just this shape that just starts from 0 and then goes up like a bell curve. And then the mean is mu, and the variance tells you like how concentrated it is. So this, compared to, for example, this guy has a smaller variance. Bell curve doesn't kind of do it justice because it tells me something about the tails. The tails go down very fast, like square quadratic, but you expect you get exponential and then negative quadratic. So tails are really, so like events that are far here are very unlikely. Things are more concentrated. So the multivariate normal is just an extension of this for a random vector. So you have a random vector, right? Y1 up to yn, the coordinates are y1 up to yn. I'll write it as it has a distribution normal between mu, which is now a vector, and I'm going to specify variance matrix rather than just the variance. Okay, and to do that, I need to give you the density of this random vector, which is really the joint density of the coordinates. So like whatever you need, the density of this would be a multivariate function, basically n base n coordinates. So this is the PDF would be a function of y1 to yn, so it lives in Rn. And what it does is if I multiply this by the like an n-dimensional volume using the probability, so I have to integrate it over to Rn over the set. And this is the formula, which may look kind of scary, but really not that complicated. So this part is the key part. So it's like exponential of negative something in there, which is the quadratic form y. And so y minus mu is centering, and then transpose times sigma inverse, the inverse of the covariance matrix. So we're assuming that sigma is invertible. And then times y minus mu, so this would be n by 1, this would be n by n. Y by n, so this is, sorry. This would be the other way around. 1 by n by 1, so we put 1 by 1. So this is really a scalar, and so it kind of like this has to be a scalar because it's just probability density. Okay. So just give me a scalar, so for any given y, this is kind of telling me exponential negative this, and then times this factor, it's roughly the probability density at that point. How likely we're going to see things in that vicinity if you multiply by the whole volume there. And this quantity here is the determinant. Okay. Determinant of sigma. And then 1/2 is just the square root, right? It's a determinant is always going to be positive, or not negative. In fact, positive because we're assuming invertible. Determinant being positive is a consequence of ESDness. Being positive semi-definite eigenvalues are all non-negative, and this is just a product of eigenvalues. So it makes sense. So this particular form of this prefactor is to make this integrate to one. Okay, the key part is this exponential. Okay. How many people have seen kind of this? Okay. In n dimensions or in 2 dimensions? Two. How many people have seen this in two? Y only bivariate normal. They go with bivariate. So bivariate will be the case where you have y1 and y2 only. And then you can just maybe simplify this. You write down sigma as, I mean, if you want, in the n equal to 2 case, you would write sigma as sigma 1 is squared, let's say sigma 2 is squared, and then often like rho sigma 1, sigma 2 as the covariance. So rho is the correlation coefficient. And then if you plug this in and invert it and then multiply out, you get the form that probably you used in the root 1 minus rho squared here somewhere. So the inverse of that matrix, when you plug in and multiply out, you get the form that you thought. This is the n-dimensional version, which is really nicer actually looking because the inverse is compactly capturing it. It tells you a lot. So unfortunately, I don't have time to dig into that. I'm going to give you some examples of what this looks like. Okay. If you set n equal to 1, you just recover because in that case, sigma will have a single entry. Like in n equal 1, sigma will just be sigma squared. And the inverse would be just 1 over sigma squared. And so this would be 1 over sigma squared, and then this transpose times that, you can just, this is where you stay there, just with it squared. So in this case, you would do this. And then you can verify that this is just that the determinant would be a sigma squared as well to this. Meaning, right? And then, but it's one dimensional, and then get this formula back. You want to like here. Okay. So far, so there's not much we can do with this, but I'm going to show you that kind of looks like. So here we have the contour. So if you set, for example, f of y equal a constant, okay, and look at all y's that for which this is a particular constant, this would give you a contour of the density. So in y2, I'm going to look at, let's say n is equal to 2. I have y1, I'm looking at all y1 and y2 such that the density is, let's say, a particular constant, fixed constant. Okay. And you can plot it, the set of all points in the plane for which this density has the same value, which means that they're equally probable kind of. And so what you get in the case where sigma, this is n equal to 2 case, when sigma is identity, so there's no correlation, then you get these circles. So things here are more probable, like actually equally probable, but they're more probable because like the color is like also the size of the constant. As you go out, they're less probable. Okay, so this is, for example, maybe f of y equal, I don't know, 0.001. This may be equal, I don't know, 0.1 or something. Okay. Or even 2 or something. The density doesn't have to be less than 1. Okay, and if I have the correlation, it would be tilted. So these are actually the level sets of the quadratic function. So the level sets of this would be equivalent in the level sets of this function. You can verify that it would be like y minus mu transpose sigma inverse. This is quadratic form. This would be some other C prime, which is related. So C prime related. The contours are determined by this kind of quantity. The quadratic form, there's the quantity of quadratic form, which would look like kind of ellipsoid. So here you have correlation 0.7, for example, and you can see again these are equally probable and height more probable in this case than outside. So as you go out, it's less probable that you find things here, but also shows you the correlation. So for example, if I see something here in the y1 axis, okay, so if I know, for example, you can get the conditional. So if I see something here, if I see y went around one, then this tells me the range of probable kind of y2. So it's more likely to see y2 around here, because it's larger, and then less here, and then very unlikely here. So this gives you the conditional distribution. And as you go along, you can see like from around 0, it's like if I see something y1 here, I get more like a different distribution. Okay. So it's more likely to find y2s in this range, as opposed to this case where if I just, for example, see y1 here versus here, kind of the range is not going to change. I mean, if we use the thing is that you have to normalize. It does look like the range is smaller, but it's really there's no shift. And when you normalize it, the conditional distribution remains the same. In this case, if you look at y1, it doesn't give you any information. It may look like this interval is smaller than that, but once you normalize to unit norm, really the distribution along this line doesn't change. Whereas the distribution here would change, and that tells you the correlation. So if I know y1, I know more about y2 than if I did it. So for example, if I'm here, like the range is going to be smaller in a sense, or kind of. I mean, that's not obvious. Then you get the sense of dependence. So have people seen something like this? No, okay. I can spend a lot of time on this, but unfortunately, this is not the main topic of this course. So if you look at the, I'll be happy to discuss more. So if you look at the surfaces look like this. It doesn't kind of maybe show as well, but it's like really, you have to imagine a mountain. Have you seen the contours? Like, so this is like a mountain, so this is the peaks at the middle and then goes down. So the 3D version, if you just this, the contours are easier. I mean, it can show as well. So it will be like elongated along one of the axes here. This one would be just uniformly spread out around the region. Yeah, so positive correlation tilts the bell towards the diagonal. And for example, like the correlated case also column, which is this line. So because of this determinant in the denominator, you can see that it just pops up a little bit higher. So if you have correlation of 0.7, then the determinant would be like this, and so less than 1 because of the factor. Well, you're welcome to try it, but this just pops it up. You can see in the picture. Maybe, yeah. The same scale, but it's not really. Anyways, so you can do it, trying to visualize this. The total volume under those curves are always 1. Right. The correlation changes the relative behavior of it. Function. So far, so good. This captures a lot of information in that kind of little formula there. The thing is that you're not going to use the formula as much. You can use it to do maximum likelihood, for example, which we may do. But from this formula, you gain a lot of properties. So we're going to use, which I'm going to state mostly without proof. So the first property that follows from that definition is that if I have a multivariate normal random variable, this is a multivariate normal random variable. I'm sorry, multivariate normal, but just normal or Gaussian, so it's called Gaussian. Just a Gaussian vector. And then in here is the dimension. So it just tells you that y is n-dimensional. So you're dealing with an n-dimensional distribution. And then A is our like non-random matrix, usual thing, n by n. B is in Rm. And I form A times y plus b. And we know how to calculate the mean and the covariance of this. what this slide is saying is that if y happens to have a normal distribution, like multivariate normal distribution, then u also happens, like, will have a multivariate normal distribution. Okay, so this operation of multiplying by a matrix and adding a constant, this is called a affine transformation. If b was 0, it would be called linear transformation, but because of the shift, if you want to be precise, it's an affine transformation. So this results really saying that affine transformations preserve normality. If you start from a normal multivariate normal random vector, you do an affine transformation, you remain in the same family. Because a normal random vector is determined by a mean vector and a covariance matrix, I just have to tell you what the mean and the covariance matrix are to completely determine the distribution, because then it completely determines the density by that formula. And you know, we have calculated this. So if you look at the mean, the expectation of AY plus B, by linearity, B comes out, A comes out, you get A times expectation of Y plus B, and we call the expectation of Y mu, so we get A mu plus B. So that's the mean. Okay, and we also know the covariance. So the covariance of AY plus B, first, if you recall, shifts don't change the covariance, so I can just drop the B. The covariance of this would be the covariance of AY. And we just did the covariance of AY, which is going to be A covariance of Y. A transpose, so I get sigma. So I get this A sigma A transpose as a covariance. So we know these from previous the calculation. What we now know is that the whole distribution is also normal. So I'm completely characterizing the distribution of this affine transformation. In order to prove this result, you have to calculate the density of this and then show that the density will look like something like this with the new mean and the covariance matrix. And to do that, you need to know how to transform densities. Maybe if people have seen this in quantum B or quantum A, how to transform densities. You want to prove how you calculate the density of it u from the density of y. Or reverse. So the formula involved. No. If I give you, let's say, y, and you want to compute the density of y squared, or 2y, or 2y plus 3. Have you seen this? The variable. There's this thing called change of variable formula. Jacobi, okay, good. So there's like this is a multivariate operation. There's a Jacobian this transform. So this would be f of y, so then let's call it f is not good thing. Some function of y and it has a Jacobian. Partial derivatives of coordinates with certain other coordinate, and then the determinant of that appears. And then the inverse map also appears. So you just divide the density at the inverse of the transform and then multiply by the proper determinant of Jacobian, and that gives you exactly what we need. You get the same formula. The determinant would just correct this prefactor. See, the role determinant of Jacobian just corrects that, and when you replace it by the inverse of your phi transformation, this remains the quadratic. So you may say that. That's just like a very brief sketch of the proof, but we don't worry about the proof. If you're interested, go look at that proof change of variable. Change of variable formula involving the Jacobian of the transformation. So if I do a nonlinear transform of y, it's not going to be normal anymore generally. But if I do a linear or a affine transformation, I'm going to remain in the normal family, which is very useful for us because quantities that we observe in regression, like beta hat and various other quantities, they are of this form in terms of the observation. And so if the observations are normal, then the beta hat and stuff, residuals would be normal. All the things that we care about would be normal. Okay, so we stay either say linear functions or either affine functions, margin remain in the same time. Okay. Like, have you seen one like dimensional variant of this? So if I give you, let's say, a normal scalar, and the value is multiplied by 2, it would be another normal value. If I add something to it, it will be another normal value. So this is the more general version. This mnemonic, affine transformations preserve normality. Affine transformations. There. Oh. What is an affine transformation? Multiplied by a matrix, adding it constantly. That's the general affine transformation. Good? Yeah.
The last word.
Okay. This one? Transformation. Transformation. Did that improve? Okay, so important special case, if I look at that quantity A transpose Y that we just looked at, the mean would be A transpose times mu because of linear, and we just calculate the variance would be A transpose sigma A, or that would be covariance matrices is 1 by 1. So what we now know that this is also going to be normal. It's going to be a scalar normal. These two we either know, or this is just blue from the top. And this tells you this is basically a general linear combination. So if A is A1, A2 up to AN, and Y is Y1, Y2 up to YN, then A transpose Y is reading summation AI, YI. So this is saying a general linear combination of the elements of a multivariate normal random vector is a normal random variable with the regular amount of machine. And this is how you calculate in the covariance. The linear covariance should be obvious, and then by this point, and then the normality falls from this result. Okay, but no useful fact. You have to be, sometimes they call it joint, like these random variables, they call them jointly normal, which means that the vector has a multivariate normal distribution. Sounds good? One more fact, which is actually really like a special case of this. This was one special case. Yeah, okay, so maybe just the preview again, as I mentioned. So beta hat is like a matrix times y, and if y happens to be Gaussian, y is going to be like our like a vector of our observation from regression we'll see. Then we know that let's say, I mean, this will be something that we assume y is a certain normal. And the vector that beta hat will also have a multivariate normal, so beta hat will be a coefficient. At least the score system at regression coefficient. Okay, we'll see this. That's how we're going to use it. Okay, so this is the second fact, which is really not like an independent fact, it's just another special case of affine transformation. If you just learn that, that's enough. But this is saying that the marginals of the multivariate normal distribution are multivariate normal. So what is a marginal? For example, if you have a vector, y is equal to, this is going to be tricky because, okay, let's do this. So you have a z, which is z1, z2 up to zn. Okay, this is a vector. Any subset of these elements that I pick, let's say I pick like z1 or z3, let's say z1 and z5, let's say this is 5 dimension. Okay, this is a subset of the elements. This is, you can think of it as a marginal. Oftentimes people, when say marginal, they mean just univariate marginal. So just the distribution of, for example, z1, the distribution of z1 is a marginal distribution. The distribution of z2 is a marginal distribution. The distribution of z1, z2 is a marginal distribution. The distribution of Z2, Z1 is also a marginal distribution. Any subset of the vectors in any order we pick, that's what I mean by marginal. Okay. So if I have a vector, I pick a subset of the coordinates, that is a new random vector that has a distribution. We call this a marginal of this distribution. The general idea. And the key here is that this random vector is also going to have a multivariate normal distribution. So all the marginals, so any subset of the elements that you pick and form a new vector, any subset of elements, gives you a new random vector that will also have a multivariate normal distribution. So the easiest way to see is that this operation is really an affine transformation. So what happens is that I can, let me do it right here, for example. So you have Z1, Z1, Z2, up to Zn, or let's say Z5. And the claim is that I can write this, there's a matrix that I can write that gets multiplied by, sorry, so I want to say what the claim is that I have this like vector I just created out of thin air. So like this is like a arbitrary like collection of indices Z3, Z1, Z5. Just a new random vector. I can write it as a linear actually transformation of the original vector. Anyone? If there's a matrix that we can multiply, I get this. What is that matrix? Coming to the first row. 0, 0, 1, 0, 0. So this is going to pick up, it's just the third element here. And you multiply this, this selects the first element. Because the linear combination that we with this, these coefficients would be this neutral. What is the second row? 1, 0, 0, 0, 0, and then the last one would be 0, 0, 0, 0, 1. So you can see that this simple matrix that if I multiply by this guy, I get this. And so this falls within this general framework. So I've written a new vector, let's say called u over z, and a times y, b here is 0. So then the result would be a multivariate Gaussian vector. And we can compute the mean and covariance, but this would be a times the mean of this would be the mean of this, which just selects the corresponding mean. So the mean would be just mu3, mu1, mu5. It's the same matrix operates on the mean. And the covariance would select the respective submatrix. So if you multiply out, covariance of z and then the transpose of this, so this transpose, you multiply out, you get the covariance of z, which is obvious once you do it because you know what the covariance of this would be. The covariance matrix of this would have diagonals which are variances and the pairwise covariances on the off diagonal. You don't need to do that calculation. So in this case, these calculations are kind of trivial. You already know the mean of this. The mean of this would be the expectation of this, which would be 3, mu1, and mu5, and then the covariance matrix you can just write down. But just the fact that this property allows you to claim that that would be normal, the result would be normal. And in fact, the covariance matrix of this would be a particular sub-matrix of the original covariance. So it would be like, if you write down the covariance matrix of the Z, the like third row, and then the first row, and then the fifth row. And then here 1, 3, 5. So the submatrix here and these rows would be after a proper permutation, because we're just reordering things as well, would be the covariance matrix of that. Oftentimes what you do is that you don't do this strange kind of combination. Maybe you partition, usually like we have a vector, let's say y1, y2, y3, y4, y5. You usually partition it in like a natural way. It doesn't have to be, but let's say I partition it into these block parts. So this part will give me one marginal, this will be another marginal, and then you can read it off the corresponding blocks of covariance matrix. So the covariance of matrix of this part will be just 1, 2. So it will be just this part. So this part of the covariance matrix would be the covariance of that. This part would be the covariance matrix of this. And then this would be the covariance. So if you partition it in a security fashion sensible way, you do, because that's what you do, then the covariances are read like this, but it doesn't have to be. So you can just permute things and still read this like the coefficients will be there, you just have to reorder them. So this guy would be the first one, and it's basically has to like permute the elements a little bit. But again, the main fact remains that you don't need to remember any of this. It's just a consequence of the fact that affine transformations are multivariate, and a general marginal can be written as a linear transformation of the original way. The rest you can easily figure out. The mean and the covariance matrices are easy, and you just get those free that this is. Questions? Okay. Not really an independent property, marginals are like that. Yeah, this is doing the block thing, which I'll leave you to figure out. So we are blocking, so here y1 and y2 are blocks. So this is p dimensional, this is n minus p, and this is often not impacted. This is like block like this, so p n minus p here. And this is like that p n minus p, p n minus p. So this is a p by p matrix. It's similar to what I did over there. But if you're comfortable with block structure, then you can just write things out in block format. So on, it's not difficult. Let's move on from this. The main thing that I want to kind of get from this is, okay, so we actually needed this. So if you do partition in like a constitutive fashion, the mean is partitioned like that, and then the covariance matrix is partitioned in a similar way. So the p by p block of top would be the covariance matrix of y1. This bottom part would be the covariance matrix of the y2, and then the cross term would be the cross covariance. So basically all the covariances between elements of the y1 and elements of y2. And so one interesting thing happens when this is 0. So when sigma 1, 2, or sigma 2, 1 is the transpose is 0, then it becomes diagonal, but block diagonal. Okay, so what happens when we have these two zeros? Then y1 and y2, these two vectors are going to be independent. And the reason why they're independent is once you write down the density factors into two pieces. So f of y would be fy1 of y1 times fy2 of y2. This might not be obvious, but you just have to plug it in. So if these blocks are 0, the inverse of this matrix would be, so the inverse would just be sigma 1, 1 inverse, 0, 0, sigma 2, 2 inverse. Okay, so how to invert the block diagonal matrix like that, and then you plug it into the formula, and then you notice that when you calculate the y minus mu inverse, like transpose sigma inverse 1 minus mu, this would be like y1 minus mu1 sigma 1 inverse if you do the block multiplication plus y1, sorry, y2 minus mu2 sigma 2 inverse y2 minus mu2. So just the quadratic form just turns it into two separate pieces, and when you take the exponential, you do next negative this. You get exponential of negative the first term times the exponential of the second term. And so it factorizes into two pieces, one a function of y1, the other a function of y2. And this is kind of the way that we can shoot two random vectors or two random variables of independent vectors with the factors. And because of this fact that this quadratic form is like when you have zeros here, it just kind of simplifies. You multiply out the block fashion, you get these two terms, and in fact, if it's not clear, do it for yourself, and if you have questions, let me know. The proof is not super important, it's just the fact that when this happens, they're going to be independent, which is a strong fact. So this is saying the two pieces, the two vectors are uncorrelated. Table 1, 2 being 0 means the two, they're not necessarily scalar of the third. This could be p dimensional, this could be n minus p dimensional, and this would be p by n minus p. So every coordinate of y1 is uncorrelated from every coordinate of y2. It happens that if that happens in the Gaussian distribution, then they're able to. Okay. The pieces are independent. This is very important to us. Uncorrelatedness in general is weaker. So independence implies uncorrelatedness, but not the other way around. But in this case, in the multivariate family, they're the same. So they're equally about it. So you can say they're independent, they're uncorrelated, they're the same in general locations. So I think, yeah, we're almost done with this. Next, I'm just gonna wrap up next lecture, and then we move on to regression. Thank you very much.